Right, so let us get started with a uniform cost search. So again, we'll try to solve the same problem that the agent is present in this cell and he needs to go to this cell with the minimum cost. And these cells that you see in orange are harmful cells. So if the agent goes inside this cell, it will reduce his life to some extent. Now, we've modeled this problem this way so as to give the agent an incentive to uh, not only save some part of his life but to also take as less number of steps as possible. So this is so the cost of going from one orange cell to another orange cell is 10. The cost of going from one harmless cell, so white is a harmless cell, so going from a harmless cell to another harmless cell is 2. The cost of going from a harmless cell to a harmful cell is 10, and the cost of going from a harmful cell to a harmless cell is just 1. So we'll start. The agent is at node 15, and we'll start from node 15, and we'll expand all its neighbors. So the agent can go right, can go up, or go left. So these are the possibilities. And now these uh, square boxes in a blue boundary that you see, these are nodes that are in something known as a frontier. So nodes in the frontier are not expanded, and they can be expanded, but all of them are put inside a priority queue. So the frontier can also be thought of as a priority queue in uniform cost search, and the priority or the order in which those elements are arranged in that queue is on the basis of the path cost of that node, of reaching that node from the source. So in this case, going to node number 11 from the source costs you 10, going to 16 costs you 2, because going from one harmless to another harmless cell is 2. The cost of going from a harmless cell to a harmful cell is 10. Now from the frontier, in each step we will choose a node that has the least cost. So in this case, we've got two nodes that have the least cost. We can expand, just to break the tie, we will expand 14, because it is the number itself comes before 16. So we'll expand 14. Now the cost of going to 13 is the cost of going to 14 plus 2. So again, from one harmless cell to another harmless cell costs you 2, and same for 10. Again, we have 13, 10, 11, 16 in the frontier, and we'll expand the one with the least cost, and in this case it is 16 with a cost of 2. Now we expand 12. So the cost of going from 16 to 12 is going to be 10, and the cost of going to 16 itself from the origin is 2. Therefore the total cost of going to 12 through 16 from 15 is 12. Now we'll expand the node with the least cost. We've got two nodes, and we'll expand 10 because it comes before 13. Now we will expand in the frontier. We've got 13 as the least cost node. We'll expand it, but there's nothing to expand because I've already seen 9, and if I go to 9, the cost of going to 9 is also going to be 6, so that is going to be 4 plus 2, that is 6. So there's no real advantage of going to 9 from 13. And if I go to 14, actually it's going to increase the cost of going to 14. It will be 4 plus 2, that is 6, which will be greater than 2. Therefore no real changes when we expand 13. After going to 5, then we expand 9, and we open up the node 5, and the cost of reaching 5 is 8. Again, 8 is the 5 is the node with the least cost. We'll expand it. and now we have two nodes with the cost of 10 in the frontier. We'll expand 1 because it comes before or it is smaller than 11. Then we've got 12, two nodes with the cost of 12. 2 and 12 will expand 2. Oops, oh sorry, there's one node with the cost of 10. So that will be expanded first because it is smaller than 12. And now the least cost is 12, and then node number 2 will be expanded now. Now I'll expand, so there's 14, 14, 20 and 12, so this one will be expanded. Now 13 is the least, so 8 will be expanded. Now if you see, 4 is the goal state, but at this stage we will not call it done. We will not say that the algorithm is done, because there might be a chance that you could reach 4 through 3, because the cost of coming to 3 from 15 is just 14, which is less than 15. If the cost of going from 13 to 4 was say 0.5, we could have reached 4 with a lesser cost than the current best. So that's why we do not expand or call the algorithm done even when we expand, or even when we have the goal node in the fringe. We wait till it has the least cost. So now we'll expand the node with the least cost, which is 14, which is 3 with the cost of 14. But there's nothing will change, because going from 13 to 14, in fact here it costs 2, so it will be 14 plus 2, that is 16. Therefore there's no point in making any change here. Similarly, from 6 to go to 7, you could go to 7, you could go to 2, you could go to 5 and 10. But to go to 7, it will cost you 14 plus 10. So 14, because it is the cost of going to 6 from 15, from node 15, and the cost of jumping from this node to this node is going to be 10. So that will be 24, which is greater than the current value. So there's no change again for 14. We'll just for 6 we'll just expand it. Now there are two nodes in the fringe, and this one, that is the goal node, has the least cost, so it will be popped out from the priority queue. And if that is the goal node, we will declare that we've reached the goal state, because there's no better way to reach the goal state. If in the fringe there's no other node that has a cost lesser than the goal node. So this also guarantees optimality. We'll discuss more about that later. So this is the algorithm for uniform cost search, and so initially we iterate over all the nodes and we set their state to unvisited and their path cost to infinity. So path cost is the cost of going from the start node to the node n, and we also set the parent of a node to null. So this will help us, so once we've reached a goal state, this will help us track back and find what all nodes are visited from the source node to reach the node n. So now we start the algorithm. We set the start node equal start node's state to visited, and start node's path cost to 0, because the cost of going from one node to itself is 0. Then we add the start node to the priority queue. So this priority queue is going to arrange nodes by their path cost in an ascending order. Now we iterate over this until the queue is empty. So we pop the first node from the priority queue, and this is again the node with the least path cost. After it is part, we check if that is the goal state. If it is the goal state, then we try to get its parents and then return its parents. Okay. And one thing you need to notice is that we do not, whenever we expand a node, so here we are trying to expand the children of the current node. So if the uh, child node is a child node, or the adjacent node of the current node is, the state is unvisited, then it means that it has not been seen as yet. So in this case, if this is the start node and this is the child node, sorry, this is the current node and this is the child node, so the cost of going from the start to current node, that is the current node dot path cost, that is going to be equal to 30, and uh, and the cost of going from the current node to the child node, which is the path of going, cost of going from current node to the child node, that is 5 in this case. So the child dot path cost, so the cost of going to the child node from the start node, that is going to be 35, and the child's parent is going to be the current node, which is this. Therefore we so this is the change that happens after this code is executed, and we set the child state to visited, and we also enqueue the child in the priority queue. But now let us assume that there is another node that is present over here, and it has a path cost of 32, so obviously it will be visited after A has been visited. Okay, so once we reach here, if the current node is this one, then um, it also has the same child as A. This was a node that we expanded before, and now in this case the child node is visited. Okay, so this code will not be executed, this portion of the code will not be executed, this portion will be executed, and now the child state is visited, which is true. So child state is visited, and the child's dot path cost, so currently the path cost for this child is 35, which is greater than the current node dot path cost, which is current node dot path cost is going to be just 32, and the cost of going from the current node to the child node, that is just 2. So the total cost is 34, which is less than uh, okay. So the cost of going to the child node through this parent is just 34, which is less than the current cost, and that is through A. So therefore we will update the state at the child node, and will change its path cost to the current node's path cost, which is 32 plus 2, that is going from the current node to the child node, cost of going from current node to the child node, and will set the child's parent to the current node. So initially it was pointing to A, but now it will point back to this node ch, and then we'll also refresh the queue, because so this is a priority queue, or we can also heapify it, but refresh is a more abstract way of saying that we need to reorder the elements of the queue considering the update in the cost. So this is how we iterate over all the adjacent nodes or child nodes of a node. We keep doing that till the queue is empty. After we have expanded one node completely, which means we've seen all its children, then we set that node state to expanded. And once we do that, there's no better way of reaching that node than the current cost. Okay. So Now let us look at the time and space complexity of uniform cost search. So this is we'll talk about the worst case. And so if you uh, assume that all step costs are the same, then uh, uniform that is the uniform worst case for the uniform cost search, because it has to keep all the nodes in the fringe, and it pretty much works like breadth-first search. So at a level n, how many nodes do you expand? So it's going to be the nodes in the first level, it is going to be the nodes in the second level, nodes in the third level, and so on, which can be written as big O of b to the power n, because for larger values of n, this is going to overpower everything else. Now let us just assume that all the step costs are the same, and the cost of optimal solution is C star, and the cost of each step is at most E, then there are C to the power E steps taken at max. So let just assume that there's S, which is equal to C star divided by E, which means that we have explored BS nodes. But the time complexity and space complexity of uniform cost search is big O of B S plus 1. And then why is that? It should be BS, it should not be BS plus 1. The reason for that is, let us try to look at this situation. So all these red nodes, nodes with red boundaries are expanded, and these with blue boundaries are still in the fringe. These without any boundaries are yet to be expanded. So the solution is present over here, and we have a state like this. So we'll next expand this node, and after we have expanded this node, we'll add these two in the fringe, and then we'll encounter the solution node, and then we can declare that, okay, I found the solution here. But if you see, the solution is at say 1, 2 and 3, the height of 3, right? Actually it is height of 2, so this is 0, 1, 2, it is at height of 2, and we have expanded nodes from the next level as well. Okay, so we actually end up expanding nodes from one level more than the level at which the solution exists. So that's why we have this plus 1, just because we expand another level. So the time and space complexity both are the same for uniform cost search. Now let us discuss about the optimality of uniform cost search. So this is under the assumption that all step costs are positive. So okay, so let us assume that considering this state, that there's a cost of going from the start node to A, which is written over here, and A also happens to be the goal node. So now obviously, as C1 has the least cost, right, it will be expanded, and it is also first in the priority queue, so it will be removed from the queue. Now if someone claims that, okay, I know a path that can take me to A through B with a lesser cost than C1, but there's a fact that C1 is actually less than C2. If that was not the case, B would have been present before A in the priority queue, and that is not the case. So this is guaranteed from this state, and it is safe to assume that C1 is going to be definitely less than C2. Now that person is saying that, okay, C2 plus X is going to be lesser than C1, but this will clearly not be possible, because X, for that to be possible, X has to be negative. right? And we're assuming that um, optimality of UCS is only guaranteed when the step costs are positive. And is uniform cost is complete? Yes, it is complete because it always finds a solution. Okay, stay tuned for the next video on depth first search.